We have been looking at Bode diagrams, right? So, and yesterday we saw what was the difference between a minimum phase and a non-minimum phase system, right? As far as the asymptotic value of the magnitude plot and the phase plot were concerned, right? So, today let me generalize it, like let us say in general you have a transfer function g of s, which is a ratio of n of s and d of s. And let us say the numerator polynomial is of order m, the denominator polynomial is of order n. So, what is going to happen is that if you have a minimum phase system, that means that of course, I want to say assuming that all the zeros are in the left of complex plane, okay, by a minimum phase system, you will see that we can generalize the asymptotic value of the phase plot. Okay. So, let me write down some general statements, and then we will discuss them. Okay. So, if we look at this transfer function, we will see that the magnitude, or to be more accurate, the slope of the magnitude plot of g of j omega would tend to minus 20 times n minus m decibels per decade, okay, as omega tends to infinity. Okay. So, this is going to be true for both minimum phase and non-minimum phase systems. Okay. So, essentially n minus m is the relative degree of the transfer function, right. So, the slope of the magnitude plot is always going to tend to a value of minus 20 times n minus m decibels per decade. Okay. So, irrespective of whether we have a minimum phase system or a non-minimum phase system. Okay. So, this is something we can check from the previous example, right. So, so what did we do in the last class? So, we immediately saw that the magnitudes were essentially the same, and if you look at it, this is like 1 plus Ts and 1 plus T1s, right. So, if you consider this, right. So, you have two factors, right. This I can rewrite as 1 plus Ts times 1 plus 1 divided by 1 plus T1s, right. So, we already know from the building blocks that as omega tends to infinity, what is the slope of 1 plus Ts? It is going to be 20 decibels per decade, right. And what is the slope of a high frequency asymptote slope? It is going to be minus 20 decibels per decade for 1 divided by 1 plus T1s, right. So, as omega tends to infinity, right. So, as we go to higher frequencies, so what is going to be the net slope? It is going to be the sum. So, it is essentially 0. So, you can see that in this case n was 1, m was also 1, right. So, you can immediately see that n minus m is 0. That is why in the previous example, we would have a slope of 0 decibels per decade at high frequency. Essentially, the magnitude curve will flatten out, right. So, that is what will happen. Okay. This is true for minimum phase and non-minimum phase systems. Okay. But the phase of g of j omega would tend to minus 90 degrees times n minus m, okay, only for minimum phase systems. Okay. So, this is an important distinguishing feature. Okay. So, only for minimum phase systems, would we have the the phase of the sinusoidal transfer function tending to minus 90 degrees times n minus m. Okay. Once again, we could observe it from the previous example, right. So, in the previous example, once again n was 1, m was 1. So, what happened? We saw that the phase went to 0 degrees, right, as omega tends to infinity for the minimum phase system, because n minus m is 0, right, for the previous example. So one can immediately observe the generalization, okay. But then like for a non-minimum phase system, we saw that it went to a value different from minus 90 degrees times n minus m, okay. So that's what happens, okay. So this is something which we will use later, you know, like that is if you conduct experiments and then like if you happen to get the magnitude plot on the phase plot, right. One could use this information to figure out the relative degree of the transfer function, because from the magnitude plot you look at the slope of the high frequency curve, you will get n minus m, right. So you will know what is the relative degree of the transfer function, correct. So because the slope is going to be minus 20 times n minus m decibels per decade, right. And then like you look at the high frequency value for the phase, you will get you will be able to determine whether it's a minimum phase system or a non-minimum phase system, right. So that information is something you can obtain, right. So we will see, you know, like when we do a case study slash project, you know, like towards the end, we will look at this thing, okay. So that's something we will do later on, fine. So let's essentially now do one example today, so that like where we construct the Bode plot of a transfer function from start. So this will illustrate the entire process, okay, like as to how to construct the magnitude plot on the phase plot, okay. So let's do an example today, right. So let's consider a transfer function which is of the form, let's say s divided by s plus 1 times s plus 10. Okay, so let's say I consider this transfer function, right. So I want to plot the Bode diagram for this particular transfer function. So obviously we need to rewrite this transfer function in terms of the factors that we have learned till now, right. So how can I rewrite it in terms of in the structure of factors that we have learned till now? Is it already in that structure? Not really, right. So what should I change? See, the s plus 10 term in the denominator, I should make the constant term as 1, right. So what do? I just pull 10 out, right. So if I do that, what's going to happen? I am going to get this, right, s by 10 plus 1, okay. So this will give me 0.1 s divided by s plus 1 times 0.1 s plus 1. Do you agree? Right. So this essentially means that I have 4 factors: a constant 0.1, a s term, and then a 1 by s plus 1 term, and then a 1 by 0.1 s plus 1 term, right. So I have to plot the individual Bode plots of these 4 factors and then get the net Bode diagram, right. So that's what I need to do, okay. So if I start looking at each term, if I take a look at 0.1, what can I say about its magnitude in decibels? So if I take logarithm and multiply it by 20, how many decibels will I get? What is log of 0.1? To the base 10 minus 1, right. So essentially I am going to get the magnitude as minus 20 decibels, right. So that's going to be constant. What about its phase? 0, right. Anyway, it's on the positive real axis, okay. So that's what I'll have. So then the second factor is s. What is its magnitude in decibels? If you recall, it was 20 log omega, right. So you have a straight line with a slope of 20 decibels per decade, right. So what is the phase? What is its phase? What is the phase of the s term? Plus 90 degrees, right. So we discussed this, okay. So the third term is 1 by s plus 1. This is a term of the form 1 by ts plus 1. So essentially we can draw the low frequency asymptote and the high frequency asymptote. What is the corner frequency of this term? Here T is, capital T is 1. So 1 by capital T is the corner frequency, right? So what is the corner frequency? 1, right? So 1 radians per second is the corner frequency for this particular term. So then the fourth term is going to be 1 divided by 0.1 s plus 1, right? So what is its corner frequency? Here you see that T is 0.1, so 1 by T is going to be 10. So 10 radians per second is the corner frequency, right? I hope it's clear how we got these values, right, for the corner frequency. So these are the 4 blocks. We just need to plot the magnitude plot and the phase plot for these 4 terms and then add them. That's it. That's all we need to do, right? So let's start from the magnitude plot. Okay, so let me start with the magnitude plot. So let us say I draw so omega, okay. So let us say I consider of course 1 and 10 are going to be my corner frequencies. So I consider a frequency range typically 1 decade above and 1 decade below the corner frequencies, like that's typically the choice of a range of frequencies that we by and large consider. It's a rule of thumb, okay. You can go for a larger range also, okay, no issues with that. So on the abscissa we are, on the ordinate we are going to plot the magnitude, okay. So the vertical axis we will have the thing in decibels. So let's say like I have 0 decibels, minus 20, minus 40, minus 60, plus 20 and so on, okay. So these are my values, okay. So let's plot each term one by one, okay. So let's start with S. So I am just going to use the same color code, like as what I wrote for the 4 factors, so that it's obvious what I am plotting, right. So let's first take the constant term, right, 0.1. So what is the magnitude plot of the constant term? You see that the magnitude of 0.1 is minus 20 decibels, right. So obviously that will remain the case irrespective of the frequency. So what can you say about the magnitude plot of 0.1? It's just going to be just a horizontal line, okay, at minus 20, okay. So this is the magnitude plot of 0.1, okay, at minus 20, okay. Now what happens to the next factor? The next factor is S. So that essentially has a magnitude plot of a straight line with a slope of plus 20 decibels per decade. If you recall what we had, right. So for S the magnitude is 20 log to the base 10 omega. So at omega equals 1, what is the value of this particular magnitude? It's going to be 0, right. So let's say I plot at omega equals 1, so that's going to be 0. At omega equals 10, I am going to have the value as 20, right. So and at omega equals 0.1, I am going to have the value as minus 20, right. So I am just plotting the values. So the magnitude plot of the S factor is going to be a straight line, okay. So yeah, essentially I am sorry, no, I am just erasing this, a straight line which passes through these points and which has a slope of plus 20 decibels per decade, okay. So this is the magnitude plot of S. So this has a slope of 20 decibels per decade, okay. So that's the second magnitude plot, right. Now we go to the third factor. okay, 1 by s plus 1. So, if you recall what we had about the factors or the form 1 by ts plus 1, right. So, once again, as I told, as we discussed, you know, like when we are drawing things by hand in example problems, in homeworks and exams, I want you to only draw the asymptotes, okay. You don't need to apply the correction, okay, as a first cut plot. Of course, in real life you need to apply the correction and get the actual plots, but nowadays, you know, like if you use the command Bode, okay, in MATLAB, okay, you will get what to say, the Bode plot itself, right. So, you just check out the command Bode, okay, in MATLAB, okay. So, let us plot the Bode diagram for the asymptotes for 1 by s plus 1. So, what is the low frequency asymptote in the magnitude plot for 1 by s plus 1? 0 decibels, right. So, if you recall what we discussed, so we are going to have till the corner frequency of 1. So, 1 is my corner frequency. So, I am going to have 0 decibels as my low frequency asymptote, and what is going to be my high frequency asymptote? That is going to be a straight line with a slope of minus 20 decibels per decade, okay. So, how do I plot it? Let us say I take a frequency of 10, I mark where is minus 20, okay, then I can plot the high frequency asymptote. Okay, with a slope of minus 20 decibels per decade, okay. So, this is the Bode diagram for 1 divided by s plus 1, okay. So, of course, when you draw, you need to essentially mark all the factors and also the slopes and other critical points, okay, like what I am doing here, okay. So, I am also indicating the slope, right, as minus 20 decibels per decade, okay. So, this is the third factor, 1 by s plus 1. Now, we need to look at the fourth factor, which is 1 divided by 0.1 times s plus 1, right. So, we know that the corner frequency is going to be 10. So, once again the low frequency asymptote is going to be the 0 decibel line. So, and then like that is going to extend till, so the corner frequency of 10, okay. So, let us say the corner frequency is somewhere here, okay, till 10 we are going to have the 0 decibel line as the low frequency asymptote. Once again, what is going to be the high frequency asymptote? A straight line with a slope of minus 20 decibels per decade, right. How can I do that? At 10 radians per second, the value is 0 decibels. If I want a slope of minus 20 decibels per decade, what is the frequency? 1 decade above 10, 100, right. At that frequency, I should have a value of minus 20, right. So, at 100, I find out, I mark minus 20 as my magnitude, and then like what I do is that I just draw a line that passes through this point, okay. So, okay, so that is my magnitude plot. Of course, the asymptotes for the factor 0.1 divided by 0.1 s plus 1, okay. Even this has a slope of minus 20 decibels per decade, okay. So, that is the slope, okay. Now, we have plotted all the 4 graphs, right. Now, what we need to do? We just need to add them, okay. So, what will be the net sum of all these 4 terms? What do you think will happen? How can I add them? So, you see that the s term is going to affect throughout all frequencies, right, and the minus 20 decibels per decade term also will affect throughout all frequencies, and the 1 by s plus 1 term and 1 by 0.1 s plus terms effects will come at the corresponding, starting from the corresponding corner frequencies, because till those corner frequencies the contribution is 0 decibels, right. So, what will happen? I have this plot for this s term, which essentially is a straight line with a slope of plus 20 decibels per decade, but that is going to be shifted down by minus 20 decibels. Why? Because I have the factor of 0.1, right. So, let me start by plotting the Bode plot till the corner frequency of 1. So what's going to happen? I need to shift the graph of the S term by minus 20 decibels. Okay, so that's what I need to do. So if I shift by minus 20 at the frequency of 0.1, the value will become minus 40, and at the value of 1, it is going to become minus 20. Okay, so that's what is going to happen to 0.1 times S, right, till the corner frequency of 1. So what I do is that I am going to use the red solid line to essentially draw the Bode diagram of the total transfer function, the net transfer function. So this is what is going to happen to my oops, what did I do? Okay. So this is what is going to happen to the Bode diagram of the transfer function at low frequencies, okay, till the corner frequency of plus 1. Now what happens at plus 1? At plus 1, the 1 by S plus 1 term starts contributing a high frequency asymptote with a slope of minus 20 decibels per decade, isn't it? Now you have, so let me essentially write in maybe pink what I am doing, okay, till 1, okay, till what to say, omega less than 1, what I am plotting is 0.1 S, 0.1 times S, right, because that is what will contribute to the magnitude plot. Between omega 1 and 10, we will have 0.1 times S plus 1, right. Now S will have a slope, contribute a slope of plus 20 decibels per decade. 1 divided by S plus 1 will contribute a slope of minus 20 decibels per decade. Both will, the slopes will just cancel off. So what will I be left with? I will just be left with a horizontal line at the same value. So in essence, my magnitude will remain constant, oops, right. So my magnitude will remain constant at minus 20 decibels per decade till I reach the slope of, till I reach the corner frequency of minus, till I reach the corner frequency of 10, right. I hope it is clear how we got this. Now what will happen after 10? From omega greater than 10, I will have all the terms coming into play, right. So I will have this 0.1 S plus 1 also starting to contribute, right. And what will be the contribution of 0.1 S plus 1? It will contribute a slope of minus 20, right. So in essence, what is going to happen is that at 100, I should have minus 40. Okay, so I think let me just quickly erase this so that I draw it properly. Okay. Okay, so just bear with me for a second. See, please use a scale to draw the Bode plot cleanly. Okay, so I am just drawing freehand. So as a result, like there is some offset. So this is the Bode diagram for the factor 1 divided by S plus 1, right. Okay, so the slope was minus 20 decibels per decade. This is the factor 1 divided by S plus 1. So what is going to happen? Now for the entire transfer function, it is going to have a slope of minus 20 decibels per decade. So it is going to go along the same line. Okay. So that is what happens here, right. So the red curve, the red solid line is for this entire transfer function, the magnitude plot of the entire transfer function. Okay, is it clear what I did? See, I just redrew the green line and so that it is to scale. Okay. See, obviously the high frequency asymptote of 1 by S plus 1 and 1 divided by 0.1 S plus 1 should be parallel, right, because their slopes are the same, right. So that is why I just redrew it to scale. Okay. So that is what I have done here, that is it. Okay. So I hope it is clear how we got this what to say, the net curve, right, for the magnitude plot. So here in the low frequency region, the slope is going to be plus 20 decibels per decade for the thing, and in the high frequency region the slope is going to be minus 20 decibels per decade. Okay, so this is how we get the magnitude plot of the complete transfer function. Okay, is it clear? Fine.